So today we are going to study about the design of flanged beams. As you would know, the flanged beam design is part of module 2, and the design is quite similar to the design of singly reinforced beams which we have already learned. So let us discuss about what the flanged beams are about. So today we shall study about the definitions of flanged beams, the different types of flanged beams, the effective width of flanged beam, how do we define it, and also how to analyze the different cases associated with the design of flanged beams. So you see this figure. This is a typical framed structure which you encounter in practice. You have a series of beams here, and on top of it you have casted a slab. And how does it happen in practice? So definitely you will be laying the reinforcement for the beams as well as slabs together, and the concrete is also poured into the beams and the slabs simultaneously. So you obtain the slab and beam as a single entity. So that is exactly what is meant here. In most RC structures, we say that the slabs and the beams are cast monolithic. That is, the slab is cast alongside beam, they are cast simultaneously. And don't you think that the slab and the beam behaves as a single structural element? So they have more tendency to behave as a single structural element, not that the slab behaves separately and the beams will bend separately. No, the flexural behavior of the slab as well as the beam will tend to behave in the same fashion because they are cast monolithically. So that is what is meant by the term monolithic. Monolithic means they are cast, constructed together at the same time, and they behave as one single piece. Okay, so we call such beams and slab portions as flanged beams. That is exactly what we call by the term flanged beam. So as you see in this figure, a part of the slab will tend to be a part of the beam itself. So the beam and this portion of the slab will behave as a flexural element, and they, when subjected to loads, will also undergo flexure or bending as a single entity. So this beam along with a part of the slab on either sides of it will be called as a flanged beam. So flanged beams are those beam slab systems wherein the reinforced beam along with a portion of the slab will behave as a single entity. Okay, and as a result the part of the slab also undergoes compression along with the compression zone of the beam while bending. Now, what are the different types of flanged beams? So as you see in this figure, we have a typical slab floor system supported by beams. So you have series of beams, on top of it you have a slab, and the end beam along with the portion of a slab on top of it will behave as a single entity, and this is a typical flanged beam. And here again you see there is a beam and some portion of the slab associated with it also behave as a single entity, and they also behave as a flanged beam. So but there is obvious difference between this one and the next one. You see, this has the shape of the alphabetic letter L, but this has the shape of alphabet T. So definitely we call them by different names. One is the L beam and the second one is a T beam. Now if you observe, T beams are generally the flanged beams which occur at intermediate positions. So these are actually intermediate beams in the monolithic beams supported slab floor systems. So this is a typical T beam. The next one, this is another T beam, and likewise the intermediate beams will behave as a T-beam. But the ones at the ends of the floor slab system, like this one, this is at the end, you don't have any portion of the slab on this side. So this will behave as a L-beam. So we call it by the name L-beam. So these are end beams in monolithic beam supported slab floor systems. And typically these flanged beams, in total we call these L-beams and T-beams generally as flanged beams. And flanged beams have two important parts. One is the web, the second is the flange. So what is flange? The overhanging parts of the slab of a flanged beam is called as flange. So you observe here, this is an L beam. The part of the slab which is overhanging, this overhanging outstanding part of this slab is what we call as the flange. So here you, in the T-beam case also, on either sides of the beam you have the outstanding portions and we call it flange. So what is web? The full rectangular portion of the beam other than these outstanding parts of the slab, we call it web. So this, the central portion of the T-beam, the full rectangular portion, we call it as the web. Here again, this full rectangular portion, we call it as the web. So every flanged beam is composed of two parts, the web as well as flange. Now it is time to define the effective width of the flange. You see, this is a typical T-beam, okay, and you don't know how much part of slab is associated with it. So you see this figure, we have marked the effective flange width here, but in practice we do not know how much part of the entire slab is part of this T-beam, okay, this flanged beam, how much portion of the, or how much extent of the slab is associated with this flanged beam, we don't know. And we don't have to worry, we have caudal provisions associated with determining the effective width of the flange, and before which we need to know how it is going to be determined. So just a curiosity. You see, this is a typical T-beam, and you know every beams when subjected to loads will experience compression in the region above the neutral axis. So if this is the neutral axis, if here is the neutral axis, the region everywhere above the neutral axis, it will be subjected to compressive force, okay. But what about the region here, the region associated with the slab? Since we said that a part of the slab is also forming a part of the beam, so the slab also experiences compressive stress, but the compressive stress on the slab may not be as high as is experienced by the beam. So that is exactly what is shown here by the actual distribution of compressive stress. You see, the compressive stress is maximum at the region closer to the beam, but as you move away from the beam, you observe that the stresses are declining, they are decreasing gradually, okay. But we are interested to find which extent of this slab is forming the part of this flanged beam. We don't know. So for which case we assume that there is some length of stress, the stress is acting for a sufficient length for which the stress is applied in a uniform way. So there is a uniform distribution of compressive stress. We are assuming it. This is not the actual one. We are assuming that there is a uniform distribution of compressive stress such that the entire force applied by the actual distribution is the same as the force applied with the help of this assumed distribution, okay. You don't have to think too much about it, just have to understand that this is the actual distribution of stress and you want to find how much length is relevant to you, how much length of slab is behaving as the T-beam. So for which you assume that there is a uniform stress distribution over this restricted length, okay, over this restricted width, such that the forces for both the cases is equal. So if you do that, you will ultimately get that the effective flange width is equal to these set of equations you will get, and you don't have to derive such equations. It is directly available to you from IS 456. If you refer to clause 23.1.2, you can say that the effective flange width, or this represents the region of the slab which behaves as a beam itself. Okay, and to find this width, just refer to page number 37, clause 23.1.2. You will find these set of equations where the effective flange width represented by the letter B suffix F, BF, is equal to L0 by 6 plus BW plus 6DF for T beams, while it is L0 by 12 plus BW plus 3DF. What is L0? L0 is nothing but the effective distance between the points of zero moments in a beam. So this is typically the span of the beam over which there is a huge change in the bending moment. You don't have to worry too much about it. If the value of L0 is directly given in the question, you just have to substitute it here. Okay, and if the given beam is a continuous beam, mostly the floor slab systems will be composed of beams which are continuous in nature. So there, if you are given the effective span in the question, just have to multiply it by 0.7. So 0.7 times the effective span will give you the L0. Okay, just substitute it here and you can find the value of BF. But you should know the other terms as well, BW and DF. So what is BW? BW, as you see in this figure, it is the width of the web. The width of the web is expressed as BW. So this may also be given in the question. Okay, what is DF? D suffix F represents the depth of flange. Okay, this is the depth of flange. So in a flanged beam, the most important dimensions are the effective flange width B suffix F and the width of the web B suffix W and depth of flange D suffix F. So you should be clear and thorough about these three important parameters using which we define a flanged beam. Okay. Now, in the design of flanged beams, we are going to discuss about two important cases when the neutral axis lies within the flange or whether it lies inside the web. The first case, where the neutral axis lying within the flange, is a very important case, but it is very simple. It is most likely to be asked in the end semester examinations very frequently. Very often you find questions from this particular case has been asked for the examination. It is very simple, and it is exactly the same way as you do the analysis or the design of singly reinforced beams, which you have already learned. Okay, so the case 1 is very important, but coming to the case 2, it is slightly complicated, where you have to deal with two sub cases as well as it given here. But you don't have to bother too much about it, because there is very less chance for the case 2 and its sub cases being asked for the examination. So most likely case 1 is very important and more likely to be asked for the examination. Okay, so let us discuss each of these cases in detail. Case 1, where the neutral axis lies within the web. Where the neutral axis lies within the flange. So you see this figure. This is the neutral axis. The depth of neutral axis is marked here, defined as XU, measured from the extreme compression fiber. The neutral axis, as you see, it is inside the flange. Okay, this is inside the flange portion. Okay, the important parameters of the flange beams BF, DF, BW are all given here. The reinforcement is provided on the tension steel. So tension steel AST, area of steel, is also given. The depth of neutral axis XU and the effective depth of the beam is also represented. Small letter D is expressed measured from the extreme compression fiber to the centroid of the tension bars. So this is a typical case where the depth of neutral axis is less than the depth of flange depth. That is why we gave it as x2 less than or equal to df. So how are we going to analyze it? You may know that this is a reinforced concrete beam wherein we have already studied that the concrete on the tension side is completely ineffective. We are more interested only in the concrete on the compression side. So whatever changes in the geometry on the tension side, that is the region below the neutral axis, is immaterial to you. It is irrelevant to you. Okay. So if you change this shape on the tension side, it doesn't really matter much to you, or it doesn't even change your equations. Okay, so that is exactly what I am doing. Instead of this profile on the tension side, I am replacing it by a simple singly reinforced beam. A rectangular beam section is what is shown here, with the parameters are exactly the same. You see the width of the flange is exactly the width of the beam provided here. The effective depth is the same as this. The AST is replicated here. The only change is in the profile on the tension side. Okay, so that I have changed. So what you can say is that just as how this beam behaves is easy to be analyzed using this particular beam, because both these beams will behave in the same way. Okay, so instead of writing down equations for this particular beam, I am going to write down equations for this one, because this is more easy and this is what we are more familiar with. This is a typical singly reinforced rectangular beam. Okay, and now you can also draw the stress distribution at limit state. By limit state I mean for a section which is either balanced or under reinforced section only, not over reinforced. Okay, so you know about the stress distribution on the compression side. The concrete has a parabolic stress variation, followed which it is uniform for some length. Okay, and it reaches the ultimate stress of 0.45 ck. All these we have already learned about. And you know the compressive force is applied here. This concrete experiences compressive force here, while the tensile force is experienced at the level of steel. And the distance between the compressive force and the tensile force, we call it by the name lever arm, represented by Z. And this also we have determined for a typical singly reinforced beam, which we know D minus 0.42 XU. Okay. Now writing down the equation for compressive force in concrete, the region above the neutral axis, C is equal to 0.36 FCK BXU is what we know, but instead of B being the width of the beam, I am replacing it by the width of this rectangular beam, that is BF. Okay, BFXU. And coming to the tensile force in the level of steel, you know it is T is equal to 0.87 Fy AST. So I have written the same set of equations here. And if you know the compressive force and the tensile force, you can easily find the depth of neutral axis XU by equating them. C is equal to T, and you get this equation which is familiar to you, 0.87 Fy AST divided by 0.36 FCKB. Okay, so once this is known to you, the moment of resistance can be obtained as equal to, mu is equal to the compressive force into lever arm or tensile force into lever arm. Okay, so this set of equations you are very much familiar with, and this is exactly the same as we studied for the analysis of singly reinforced beams. So if for the numerical problems or for theory questions, if you encounter this kind of a beam where the depth of neutral axis, if you obtain to be within the flange, inside the flange, or if you say XU is less than or equal to DF, that is the depth of flange, then in such cases we just have to transform this section into a typical singly reinforced beam and analyze it just like a singly reinforced beam. Okay, so this is very easy, and this has more chances to be asked for the examination. This was repeatedly asked for many end semester examinations, and if you observe the previous year question papers, you will find that such questions have been asked repeatedly. So it's very simple. You don't have to worry seeing the profile of this flanged beam, just have to transform it and evaluate. That's it. Okay, so this is applicable only if the depth of neutral axis is less than the depth of flange, or the neutral axis lies within the flange. Okay, now coming to the second case where the neutral axis is lying inside the web. You see that this is the neutral axis, this is lying inside the web. Okay, and you have to analyze it. And here we are going to discuss two important sub cases. The neutral axis can lie within the web, but there are two cases to be discussed here. Okay, and what are these two cases? The first case being, you see this figure, you have this T-beam given and the depth of neutral axis is greater than the depth of flange, or the neutral axis is lying inside the web. Okay, so what you are going to do, just have to separate, you just cut it off here and here, and you get this rectangular beam, and this remaining flange portion also you have, and you are going to draw the stress distribution at limit state separately for this region, this rectangular region, and separately for the flange region. Okay, and you say now that this region I am calling by the name, this rectangular portion I am calling by the name web, although this is the web, the region below the slab is the web. We are, for the time being, I am calling this rectangular portion as the web, and these outstanding portions we call it as flange. Okay, for the time being. Now you see I am drawing the stress distribution for web as well as for the flange. And for the web, this is a typical singly reinforced beam, and you know the stress distribution which we have already learned. I am drawing it here. Okay, so this initial portion above the neutral axis, it is a parabolic region, and after which it is a uniform stress equal to 0.45 ck. Okay, now you see initial portion of the stress in the concrete is a parabolic region, after which it is going as a uniform distribution. This uniform region has some length. Okay, and how much is it? You know that this is xu, this is the depth of neutral axis, xu, and this length over which the stress is uniform is roughly equal to 0.43 xu. So bear it in mind, this is 0.43 xu. Okay, so this length over which the stress is uniform is 0.43 xu. Now, as we said, two subcases are arising. So for the first subcase, if this portion 0.43 xu is greater than the depth of flange, so this is the depth of flange, and this portion of straight line or the uniform stress is exceeding the depth of flange, is the first subcase. Okay, and the second subcase we will discuss later, that is this straight line portion or the uniform stress region 0.43 xu is less than df. Okay, so there are two cases when 0.43 xu is greater than df and 0.43 xu is less than df. So let us discuss about each of these cases separately. So the first case is 0.43 xu is greater than df. So that is exactly what is given here. 0.43 xu is greater than or equal to df, or you can rearrange it like this: df by xu is less than or equal to 0.43. So it is up to you. If you want to rearrange it, you do it, otherwise don't do. Okay, now so this is the distribution inside the web, and similarly you should get a distribution inside the flange also. Okay, inside the flange, you know that here the depth of flange is only up to here. Okay, and the stress is even uniform beyond it. Okay, so which means that inside the flange also the stress is uniform like this, as shown here. The stress is uniform inside the flange. So the entire region of this slab or the portion of the flange is experiencing uniform stress equal to 0.45 FCK. Okay, so separately for web if you write, and for flange you can write, you know that the region of flange is only up to here. You don't have to draw the distribution beneath this region. Okay, so the flange distribution, it is just enough to be drawn up to here, up to the level of flange itself. Okay, so this entire region inside the flange is experiencing uniform stress, but in the web the initial portion is up to the depth df, it is uniform, and even further also it is uniform up to here, and beyond which it is parabolic. Okay, now you are going to, you know that the compressive force in the flange is different from the compressive force in the web. Okay, from this equation, from this figure itself, it is clear the compressive force in the web as well as the flange are different. Okay, and you have to write down the equations separately for web as well as flange, because you know the moment in this, the moment is being resisted by both web as well as flange. So the contribution of flange as well as the web is required to be found out, and you just have to add them up. Okay, so you write the compressive force here in the flange. You see the figure in the for the flange, the stress distribution flange is given here. You are going to write the force in flange. So force in flange is equal to, you know how much is this? This is 0.45 FCK, and you know how much is this? This is df. So 0.45 FCK into df. So that is written here, 0.45 FCK into df. Okay, and what is this? Bf minus bw. It is nothing but, you see here, this entire width is bf, but this width is bw, the width of web. Okay, so it actually represents the width of, effective width of the flange portion. Okay, so this is actually the original flange region. Okay, the region shown in red color. Okay, so the width of the region shown in red color is exactly what is shown here, because we are writing the force equation only for flange, only for these red portions. Okay, so you need to know the area as well as the stress. So what is the area? Bf minus bw will give the this width into what is the depth, that is df. So bf minus bw into df, which gave you the area, and area into stress will give you the force. So what is the stress over this entire depth? It is 0.45 FCK. So that is what is given by the compressive force in flange. Cf is equal to 0.45 FCK bf minus bw into df. Okay, so I recommend you don't by heart these equations. If you obtain this kind of a sub case, just draw the stress distribution first separately and write down the compressive force for flange as well as web from it. Okay, so the flange portion, you knew how to find it out. The actual length of the flange you have found out. The actual length of the flange is what is shown by the red color region. The width is bf minus bw will give you the length of this region into depth of the flange, df will give you the area. So this is area, this is area, and just have to multiply by 0.45 FCK, that is the stress over the entire depth of flange. Okay, will give you the compressive force in flange. And similarly you can write the compressive force in web, Cw. That is very easy. You know that inside the web the entire distribution resembles that of a singly reinforced beam, and you know what is the compressive force in a singly reinforced beam. That is nothing but 0.36 FCK bxu. So instead of bxu, just have to replace it by the width of web. What is width of web? Bw. This is the width of web, Bw. Okay, now this is clear. Compressive force you have determined. Now you just have to find the tensile force. Tensile force is imparted only by the steel reinforcements here. So that is very clear. It is 0.87 Fy ast. So you know the compressive force at the level of web, compressive force at the level of flange. and you just have to add them up to determine the total compressive forces. So total compressive force is given by Cf plus Cw. Okay, Cf plus, if you sum them up, you get the total compressive force, and you equate it to the tensile force to obtain the depth of neutral axis. You know how to determine the depth of neutral axis from this expression. Okay. Now, how do you find the moment of resistance here? So here, unlike the previous cases, we have divided the T-beam into two parts. One is a flange part and second is the web portion. The flange portion is also contributing for moment resistance, and web portion is also contributing towards moment resistance. So the moment resisted by flange as well as web you have to find out. Okay. The moment resisted by flange portion is equal to the compressive force at the level of flange into the lever arm posed by the flange. Lever arm due to flange is given here, is d minus df by 2. So d, this is d, okay, minus df by 2. What is df by 2? Half this depth of flange. Okay. So why did we come to that? This is the flange, the diagram for flange. The compressive force is acting at midway here. Okay. So midway here means it is at a distance of df by 2 from the extreme end, and you know that this much is d, and d minus df by 2 will give you the lever arm for flange. Okay, so just have to multiply the compressive force at the level of flange with the lever arm for flange, d minus df by 2. Okay, and that will give you the contribution, the moment resisted by the flange, and separately you have to find the moment resisted by the web. That also you have the compressive force at the level of web into lever arm for web. So for the web portion, it is similar to that singly reinforced beam, and you know that the lever arm for web is d minus 0.42 xu. This is already discussed in singly reinforced beams. So just multiply the compressive force at the level of web with the lever arm for web, d minus 0.42 xu. Okay, so you add the contribution of both the web and the flange, you will get the moment of resistance of this T-beam. Okay, now coming to the subcase 2. Subcase 2, you observe, we already said that in subcase 2 the uniform stress region 0.43 xu is less than the depth of flange. So I am drawing only flange here. Just observe the T-beam is the same as the previous case. I am just drawing flange here. Just you can refer to the previous slide also if you have any confusion. So I am just taking the flange portion for assessing the next case. Okay, so this is the flange portion, and the depth of flange is given df, and in this subcase 2 we are going to discuss a case when the straight line stress region, that is 0.43 xu, is less than df, which means that inside the flange portion there is a parabolic region also. So unlike previous case, here inside the flange portion it was purely a rectangular region. Okay, but here we are having a parabolic region also inside the flange. So this here arises a situation where the straight line stress region, the 0.43 xu, is less than depth of flange. Okay, so just bear in mind. So this we are going to find it using the same set of equations, but for the time being, this parabolic region will make our analysis complex. Okay, so it is very difficult otherwise to evaluate the contribution of this parabolic region in the flange. So for our convenience, what we are going to do, the flange portion we are defining a new stress distribution. Okay, we are going to define a new stress distribution which is rectangular in shape like the previous case itself, so that our analysis becomes easy. Okay, everything else is the same. The web portion, you have the same stress diagram, but in this subcase we are changing only the stress distribution diagram for the flange, because there is a parabolic region also coming inside the flange. So to avoid it, we are replacing this stress distribution by something like this. But here you observe that here the distribution is uniform, but it has a reduced depth. Okay, it is less than the depth of flange. It is less than the depth of flange. So how far is this distribution a uniform distribution? So that is exactly what is defined by y suffix f, yf. Okay, yf is equal to 0.15 xu plus 0.65 df. 0.15 xu, where xu is the depth of neutral axis, which you would know, and df, what is df? The depth of flange. And if you substitute it here, you will get the depth over which the stress is uniform. Okay, so once this is known, you can easily find out the equations. You know, the compressive force in web is the same, 0.36 FCK BW into XU. We are writing the same expression here, 0.36 FCK BW into XU here. And coming to the compressive force in flange, we are going to write the same equation. Instead of the depth of flange here, we are going to write yf. Instead of df, we are going to write yf. So that is exactly what is given here, 0.45 FCK bf minus bw into yf, where yf is the reduced depth. Okay, reduced depth of the stress block. And yf we have already defined, it is 0.15 xu plus 0.65 df. Okay, now the tensile force is the same, 0.87 fi ast, it doesn't change. And now you have separately found out the compressive forces in flange as well as the web. Just have to add the forces in both web and flange to obtain the total compressive force and equate it to the tensile force. So from this expression you can determine the depth of neutral axis xu, and moment of resistance is the same way. It is just determining the contributions of moment resistance by web as well as flange separately, that is Cf into Zf plus Cw into Zw, where the Zf and Zw, the lever arm in flange as well as web, are also given here. So it is the same as the previous case, the only difference is the depth of flange, df, is replaced by yf here also. Okay, so everything else is same. The equations are similar, okay, as in the subcase 1. The subcase 2, the equations are the same as the subcase 1. The only difference being the depth of flange df is replaced by yf. Okay, now once we determine the depth of neutral axis, the moment of resistance, it is easy to compute the rest. You can make use of these set of equations both for the analysis as well as the design, and the design steps are exactly the same as the singly reinforced beams. So now you go through this lecture once again, get your doubts clear, draw down the figures and expressions, take down these expressions and try to understand the meaning of these equations thoroughly, and now solve the quiz. Thank you.